Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so we're delighted to host Dmitry Erhan here today, who is coming to us from University of Montreal. And he will be talking to us about the latest and greatest from the exciting world of deep architectures. He has been to a number of places, including our very own MSRC in the past, but mainly he's spent time at the University of Montreal. And then before that, he did internships at MSRC and Google and at Max Planck and Helsinki University of Technology. And here's Dmitry.
All right. Let me just hold on so that I get the timing right. All right. This was not purely for the animation. So I'm Dmitry Erhan. I'm from the LISA lab. This is headed by Joshua Bengio at University of Montreal. And this is going to be I'm going to be presenting work on deep architectures and trying to understand them and trying to understand the effect of unsupervised pre-training. And I've done this work jointly with a couple of people, Aaron Courville, Joshua Bengio, Pierre-Antoine Manzagal, Pascal Vincent, and Sami Bengio. So let me see if that works. That works. Excellent. So here's a brief outline of what I'll be talking about. I'll be starting with an intro to deep learning and why we want to do that. I'll be going with kind of a brief motivation for my work, for the work that I've been doing over the last couple of years. Namely, it's work that that can be resumed by these two questions. Why does unsupervised pre-training work for these deep architectures, and how does it work? And if we have some time, and I think we have some time, maybe I'll go over some of a more speculative work on analyzing deep architectures, and I'll show you more pretty pictures since you seem to like them, and I'll end with some discussion and concluding remarks. So deep learning motivations. I think one of the first motivations for deep learning comes from this the fact that we take a lot of hints from the way the brain works. We know it's a kind of an intelligent machine, and machine learning researchers have over the years have done a certain number of copy pasting from there. So why not take a hint from the fact that there are sort of many layers of nonlinear processing units in the brain. And so we can call the brain a deep architecture under some sort of vague hand waving. Perhaps a more convincing argument is the fact that we as humans tend to organize our ideas, the way we think about the world in a kind of a hierarchical fashion. So we tend to, through composition of simpler ideas. So this can be seen in the way we learn things. We start with learning simple concepts. We kind of do a bit of scaffolding. We learn more complicated concepts. The way we think about abstractions in the real world, we tend to kind of do some sort of decompositions into simpler abstractions, less abstract things. And in the way we solve problems, we do problem decomposition. We solve problems by, a kind of an engineering approach to solving problems would be to solve simpler problems first, and to solve the complicated problem by building up on the simpler ones, on the simpler solutions. So perhaps a bit more of a machine learning argument that my advisor, Joshua Bengio, seems to make quite often is that in certain restricted cases, if you make certain assumptions, perhaps unrealistic assumptions about the classes of functions that you're trying to learn or trying to represent, there are certain classes of functions which can be compactly represented with k layers of nonlinear processing units, which is what we're going to call a deep architecture, by the way. And which cannot be represented efficiently. So they need an exponential size of these processing units when you restrict yourself to layers that are of size, not of size, a k-1 number of these layers.
That's an existence proof?
That's an existence proof, yes. Yeah, basically. There exists a function, yeah. Okay. If you restrict yourself to kind of linear threshold kind of units, or kind of binary units. It depends on the class of functions. So this kind of result, I particularly don't think it's maybe an existence proof for this kind of result exists if you don't restrict yourself to the if you have like sigmoidal units or something like that, and you don't restrict yourself to the number of these units, I don't think this is actually true. But I think for realistic kind of functions that you're going to be trying to learn or represent, actually, is this is my intuition. This is actually true as well.
Does it depend on what kind of nonlinear units you have?
Yeah. It's a linear threshold function, so it's nothing too fancy. The other kind of more machine learning type of arguments for doing deep learning is that local features or local kind of representations that you're trying to learn of your data don't really seem to scale well to problems with many variations. And by that, I mean problems where perhaps you're trying to learn a complicated decision boundary, where if you have a complicated decision boundary, and the kind of features that you're trying to learn are features that operate only in the vicinity of your training data, then you're gonna perhaps need a lot of data. And these kinds of problems are what I would consider interesting problems in life. Where if you have a simple decision boundary, then it's perhaps not an interesting machine learning problem. And conversely, a distributed representation, as opposed to kind of a local representation, they seem to be necessary to achieve this kind of generalization beyond the local features that you're going to be getting if you're just looking at the training data in this vicinity. Yes.
Are you being local in feature space or local in some sort of index set, like over the image?
I don't really know what local in the index, but it's local in the local in the input space.
Okay.
So there's a bunch of arguments that Yann Lequin and Yoshua Benjo have made about this. The interesting thing is that the nice thing about deep architectures that have these deep representations that are distributed is that in the end, what they allow you to do is they allow you to share statistical strength by kind of making it possible to reuse the features that you learned at the level k-1 for learning the features at the level k. So you can see this as kind of multitask learning if you want. If you were to do multitask learning, the kind of sense that Rich Caruana has done, and you were to learn a task, one. It makes sense to reuse the features that you learned for the task 1 to learn a task 2 if that task is somehow related. And the same kind of argument can be made for learning features. You consider learning a feature as a task. So if you learn a high-level feature, yes.
Can you elaborate on the non-local generalization? I mean, local to what? I understand that it's local in the feature space, but local to what?
Local, close to the training data.
You want to generalize far away from the training
Yes.
data? Okay. But far away from the training data, the assumption is the distribution is negligible because the training data is sampled ID from the distribution. So why do you care about generalizing where there's no mass?
You're training because you want to generalize far from the training data because the training data cannot possibly in general capture all the possible variations of what you're trying to learn. So you're going to try to kind of impose a complicated prior on the kind of distributions that could arise, and you want this prior, the kind of function, the kind of class of functions that you're going to learn to not simply be restricted on the neighborhood regions that are close to your training data, because it's not going to be possible. You're not going to generalize to anything interesting if you don't have data. So I think it's more of maybe a philosophical kind of question of whether you should be aiming to generalize far away from the data or not. And I think sort of the argument is that we're trying to make is that you should be able to. I don't think there will be an agreement. I understand your point. But I think in sort of a limited kind of data scenario, where you make some sort of assumptions that you do want to generalize away from the data, you would want some sort of priors on the way in which you're going to be generalizing away from the data. That is not simply shrink my parameters to be 0 because I don't have any data in there. So hopefully I convinced you that deep distributed representations are desirable and have some sort of more expressive power than if you just don't use deep distributed representations. The question is, how do you actually achieve such representations? How do you train? So before 2006, fully connected deep networks were not especially popular. And it's not exactly a mystery to me why, but I wasn't there. In the 90s, I didn't do machine learning. I was in high school. Sorry. Maybe that's like a dip in my chances. But I think there's a certain number of hypotheses, and you can feel free to add some of these. I mean, I'll add them to my list. But I think that one of the main ones is that the problem, in theory, the problem becomes more non-convex, harder to solve if you want to train a deep, a multi-layer neural network. And there's simply many more local minima as you add more layers. And since you're using these kind of stochastic gradient methods, by using gradient methods, you're in a multi-layer neural network, you have this problem of kind of vanishing gradients. Your credit assignment problem becomes even more complicated. So there's also the kind of universal approximation theorem, which states that for some a certain class of kind of not all the possible functions in the world, but certain smoothness assumptions, you can approximate. You can represent basically any of these functions with a one-layer neural network. So basically, why bother? And then there's people who invented SVMs and convex, and they were all nice, and they performed better than one-layer neural networks. So I guess people just kind of threw these things away. That's my history of machine learning of 20 years, but for neural networks. I think the only kind of deep neural network variety that stayed out there and that kind of evolved was the convolutional neural networks of Yann LeCun. But they had one, they were not fully connected. They had this constrained topology and connectivity, and that seemed to have made all the difference. It was easier to actually train them. It was possible to actually train these networks, and even though they had like a pretty large number of layers. So what happened in 2006 is that Jeff Hinton and collaborators, they used unsupervised pre-training. So they just used unsupervised learning to initialize these networks, these fully connected networks. The kind of algorithm that they use is restricted Boltzmann machines, and it seemed to work. So the question is going to be why this actually happened. Before we get to that question, just a brief overview of what restricted Boltzmann machines are. It's a simple graphical model with visible units x and h hidden units. It's a bipartite graphical model. So in which there's efficient inference and sampling. Inference is simply a matrix multiplication, basically, followed by a sigmoid. So that's nice for a graphical model. Since basically the conditionals p of h given x are factorial, it's easy to sample, and easy to do inference. You trade off the fact that learning is very hard in principle, since you need to kind of compute a normalization constant here, which you need to. It's going to be very hard if you're just going to do it for anything that's kind of a non-trivial model. So what people like Jeff Hinton and others have done is that they use contrasted divergence and many other variations of from MCMC literature. There's a whole industry kind of these days on kind of taking from those literature and applying this to RBMs. It's basically essentially either approximations of the gradient of the likelihood or some other ways of doing smart sampling. It's fast and it's simple. It involves contrasted divergence at its simplest. It involves 3 matrix multiplications and twice you sample twice. So it's easy. It's easy to do many iterations of this contrasted divergence. It's these RBMs have been extended to real valued units. So this kind of model here presupposes that the x's are binary valued and the h's are binary valued. You can extend this to kind of arbitrary real valued visible units and hidden units. There's been extensions to semi-supervised learning. You can have the label here. It's sort of efficient if you want to. Another way it's a deep belief network is simply a way of turning these restricted Boltzmann machines into algorithms for iteratively learning the weights of your deep neural network in an unsupervised fashion. So you're going to take this restricted Boltzmann machine, which you're going to be learning the features. You're going to be training this RBM on your training data. You're going to figure out some set of features that is interesting, that somehow perhaps captures this distribution of your training examples. You're going to fix the weights in here of this RBM. You're going to do a sort of a forward propagation. You're going to find basically p of h given x for each of your training examples. You're going to learn another reciprocally Boltzmann machine on top of it that is basically going to model the features that you just learned. You're going to do this until you're finished, which is in many cases 3 layers. So a lot of people say it's not very deep, but I'm not going to go into that. Once you're done, you basically have a way to generate as well, but to figure out what is this deep distributed representation at level 3, given the input for each of your inputs, not necessarily from the training data. And you can use the weights that you just learned, the parameters that you just learned, to initialize the network, the supervised network, and then you can just do backprop afterwards. So, or you can do like Jeff Hinton, you can do some sort of a fancy RBM here, it has a label. There's many ways to do this, but it usually involves kind of a 2-stage process where you do unsupervised learning using this kind of weird graphical model, stacking it greedily, layer-wise, and transforming this into a deep belief network. Another way of doing this is this so-called stacked denoising autoencoders. This is what we use mostly in our lab. I personally find them quite an interesting model. So they're inspired a bit by the classical autoencoders from neural networks about 20, 25 years ago. And a classical autoencoder is simply, it's actually pretty similar, kind of, just mechanistically speaking, it's very similar to a reciprocally Boltzmann machine. It's where you simply try to predict with a 1-layer neural network. It takes as an input some x, and it tries to predict x as well. So it will take x, compute some hidden representation, which is simply sigmoid of wx plus c. It will reconstruct either using the same matrix, the transpose, or some other matrix, doesn't really matter. And it will try to minimize the loss between the reconstruction and the original input x. So that's a classical autoencoder. It's nonlinear, so it's not quite the same thing as a PCA. It will do something different qualitatively. The trick here, the denoising autoencoder, is that instead of feeding to the network the original input x, you're going to try to feed it a corrupted version of this input. So you're going to try to, in some sort of stochastical way, corrupt the x, and instead, and you're going to do the same thing. You're going to reconstruct, but instead of and the kind of loss that you're going to be doing is you're going to try to minimize the reconstruction error between your x tilde and the original x. So you're going to try to make your network learn how to predict parts of your input from the others. So you're going to basically make your model more robust. And in theory, this is going to give you a better model of your data. I mean, if your parts of your input are predictable from the others. If they're not, then your task is very easy in a sense. So interestingly, this kind of model handles a variety of learning problems which are, sort of as an afterthought. Oh, well, this also handles missing values. If your inputs somehow don't have missing values, or you can, stochastically make missing values, and then your model is going to be able to predict the missing values. You can have like sort of occlusion, if you're trying to reconstruct images, or kind of multimodality. Instead of here having just an image, maybe you have an image and a text, and you corrupt the text part, and you try to reproduce it. Anyways, so depending on the kind of domain that you're going to be using, you're going to use either some sort of reconstruction error, a mean squared error, or cross entropy. Doesn't really matter. I mean, for sort of analysis of this algorithm. And the stacking, how to make this deep, is the same thing. You're computing for each of your inputs the representation. You use this representation to do this a second layer of denoising autoencoder. You do this until you're satisfied. You add a supervised softmax layer, do backprop, and obtain as good or better results than if you do a deep belief network. So I find this model a bit conceptually more simpler to look at. People who do graphical models find reciprocally Boltzmann machines simpler to look at. It's really
Your model isn't generative, though, is
it? You can make a generative sort of, but it's not. Yeah, you can't really sample from it. But if your goal in life is to do classification, then having a generative model is perhaps not necessarily useful. I mean.
And when you, because I don't actually go back and read Pascal's paper, but do you actually, when you don't add noise to the H, you sort of propagate the noise up when you do?
When you compute, you mean when you add a
layer,
you forget the noise. So the noise is only during training.
Right, but now you're going to train the next layer.
Oh yeah, you add the noise here. Yeah.
So you have a noise model at every layer.
Yes.
Okay.
Yes. But then, like, of course, there's no notion of occlusion or anything like that in the hidden layer, unless you somehow made your model like that. So it's less interpretable but still the kind of the main gist of the argument remains. You're making robust model, your model more robust. So you're trying to predict other parts of your input, be they actual inputs or representations of those inputs from the other parts. So using these and other things, there's plenty of other ways to do this unsupervised learning of networks. People have obtained a lot of good results on a bunch of kind of data sets, from MNIST to natural image patches, learning and generation, object classification with more and less realistic kind of objects, NLP tasks. I don't know if Ronan was here, and Jason Weston, or if you've seen them at NIPS, they've been quite forceful about their results on sort of name entity recognition, stats like that. Speech, music, classification with convolutional debrief networks. This is work by Hong Lek Lee and people from Andrew Ng's lab. Mocap, learning and generation, so motion capture. I don't know if you've seen Jeff Hinton's chicken dinosaur walks generation at NIPS. It's also kind of fun. So people have applied this in kind of a variety of settings. And it's not quite clear whether, at least 2 years ago when I started doing this kind of work, whether this was well understood or why this whole business about initialization, the network, actually works. So the recipe, as you've probably seen, or as I've tried to actually describe, is that you're doing layer-wise unsupervised learning, or layer-wise learning of unsupervised nonlinear features, followed by supervised learning. So that's the basic recipe. That's how you do debrief networks most of the time. And this has been applied to restrictive Boltzmann machine, more general Boltzmann machines, autoencoders, denoising autoencoders, sparse autoencoders, sparse denoising autoencoders. There's even been a paper by Lawrence Saul and one of his students about using kind of deep kernels or stacking kernel PCAs, which just doesn't sound very efficient, but it works. It actually works. I was surprised. And the question is, why does this work? And so some of the stuff that I was doing over the past couple of years is trying to attempt to untangle the various effects that contribute to good performance. So I'm going to try to verify some of these hypotheses in a kind of a large-scale setting with many hyperparameters, with kind of a bigger data sets. I mean, large scale is all relative. Maybe it's large scale. Large scale by our standards, maybe medium scale by your standards. And the goal is to try to kind of demystify a bit deep architectures. There's been somewhat of I wouldn't say backlash, but you can see this sometimes in reviewers' comments that they understand they understand that they work, but they don't really understand why they work. So try to demystify a bit what's going on. Try to present some coherent arguments for why they work, and infer maybe something useful for the future research in this field. So the plan, it's a scientific kind of plan, is to propose some explanatory hypotheses for why things work, observe the effects of pre-training in various kind of settings, and infer the role of pre-training, since this seems to be the crucial ingredient in this whole recipe, and the level of agreement of the results that we obtain with these hypotheses. And I'm going to present the hypotheses straight away. They're very simple. There's nothing too complicated about them. The first one is the regularization hypothesis, which basically states that, well, the unsupervised component constrains the network to have good features of P of x. So it constrains the model, the parameters, to model P of x well, either with RBMs or with denoising autoencoders or what have you. And it says that the representations that you get with P of x are going to be good, since you're going to basically share the parameters, are going to be good for P of y given x in a generalization kind of way. The optimization hypothesis states that, well, unsupervised initialization, what it does, it initializes near a better local minimum of P of y given x. So better local minimum, more of a training criterion kind of statement. And what pre-training helps you do, it allows you to reach lower local minima not achievable by random initialization, a standard kind of way of doing deep networks. And an interesting thing is that we're going to discover is that these hypotheses, though they sound like maybe they're at odds with each other, they're not necessarily incompatible in certain scenarios. Yes?
Question about your use of the term local minimum.
Yeah.
We often don't train neural networks until they're actually stuck at a local minimum.
Yeah.
We often stop them early or do something else.
Yeah.
By local minimum, is it okay if I just replace that with basin of attraction?
Yeah, we're going to use that.
Is that going to work?
No, we're actually going to use local minimum in here. What we mean is a better local minimum of the training criterion. We're going to use the basin of attraction. It's kind of a weird notion. What is the basin of attraction of gradient descent? I guess we'll get to that. But literally here, what we mean is unsupervised initialization gets us better training error. So in this sense, it's a better local minimum in this from this point of view.
Just say near. Right.
Yeah, because it's very hard to actually verify that we're a local minima in a neural network.
Well,
I mean, it's
very specific, right? The opposition hypothesis assumes that deep networks trained without pre-initialization are underfitting, right? And therefore,
yes.
Yeah.
Yes.
So
yes.
he's saying that they will be. That's a hypothesis. Yeah.
So that's the two rather different statements of what's going on, and we'll jump straight into that. Once I can get my slide working.
Quick question?
Yeah.
All right, so during the supervised training, all of the weights are manipulable, right?
Yes, everything is manipulable, yes.
So how does it actually constrain the network to, I mean, it doesn't sound like there's any constraint.
It
starts it somewhere.
Yes, well, we're going to see that this is a very, very, very tough constraint. Because you're doing, one has to remember that you're not doing convex optimization here anymore. So, if you were optimizing kind of a convex, you're doing kind of convex optimization, it doesn't really matter where you start from. I mean, one way or the other, if your kind of optimization problem is well set up, you're going to reach the local minimum.
Like the constraint is sort of like moving towards the minimum that's near P of X. I mean, it's like picking. It's
picking the basin of attraction. So I'm sort of, yeah.
So since you begin by just looking at P of X,
Yeah.
you claim that this is going to help you optimize P of Y given X. Now, I'm not exactly sure how you define your model, but if you said Y or exactly the complement of Y, so if you flip all the labels, it seems that P of Y of X would be exactly, for your minimum would become maxima and vice versa. But you're not using that information in your initialization, so your pre-learning step should be equally good for P of Y given X and P of minus Y given X.
I mean, yeah. I'm not quite sure what, like, are you saying that basically, well, since we're doing P of X and we don't know anything about Y,
you're claiming that you get a better starting point by looking only at X and not at Y.
Yes.
Which would mean that you're claiming that the good starting point for any given set of labels is close. So you're saying there's a region in the space where you have very, very high peaks and very, very low, and then there's other places that you want to avoid. So you want that very high Lifshitz coefficient area.
I think I agree. I think yes, but yeah. So I guess I'm not. I didn't think of what you just said, but yeah. I think the statement also says that. All questions done?
One more question here.
Okay.
Well, from the literature, I saw there are two kind of group of pieces of work that actually does the supervised learning. One is simply just doing this pre-training.
Yeah.
And then you just put this entire weight into multi-layer perception, you do backpropagation. And the other one is to do supervised training right within the deep belief network.
You mean at the top layer kind of thing?
Level.
Yeah.
So do you explore both of those?
No, we don't. I mean, we've empirically we found that they kind of do work the same way. I mean, they give the same kind of results. So we stuck with the simpler, from my point of view, simpler kind of. I mean, it's basically just taking the same network and adding a softmax layer. So.
So you think all the conclusion you get from here is going to be applied to the other?
At least for DBNs, yeah. Because with the kind of conclusions. The same kind of framework, we applied it for both DBNs and stacked denoising autoencoders. And with stacked denoising autoencoders, there's no equivalent, it's only backprop that you can do at the end of the thing. So the setup is simple. It's MNIST, handwritten character recognition. So this is two data sets. One is a data set where we can iterate many times and until we reach some sort of local minimum, we reach basically 0 training error. Very, very fast on this. And infinite MNIST, which is basically a way to, by Gaël Losley, and I think it's Léon Botou. Yeah, Léon Botou's student, maybe. It's a way to generate elastic deformations on the fly from MNIST digits. So you can sort of generate. It's not a completely IID 10 million examples kind of data set, but it's large and somewhat interesting compared to MNIST in that you can't really go many times. So we tried 10 and 30 million examples. That's what I mean. That's what I mean by large scale. So we did 3 models, the 2 that I just presented, DBNs and static denoising autoencoders. DBNs were trained with a classical contrastive divergence algorithm. It's one step of kind of Gibbs sampling. Static denoising autoencoders, again, the way that I just presented. And models with 1 to 5 layers without retraining. So randomly initialized using, sort of the standard way of initializing neural networks as preached by Yann LeCun maybe 10 years ago. And then we tested very, very many hyperparameters with many, many seeds, just to be sure of the, yes?
So one critical thing is, are you using, for the supervised training, are you using MSE or cross entropy at the end?
At the end is cross entropy. I think, we always use cross entropy for, so we're going to jump straight into the whole observing the effect. So we stated the hypotheses. We now look at what pre-training does. So the very simple effect of pre-training is just observing the generalization error. So if you just select the best validation error, you look at those models, you sample very many instances of those models, so different random initialization seeds, and you do denoising autoencoder pre-training and no pre-training. You vary the number of layers, and you look at the classification error for both of them. You can see that qualitatively they behave differently. So as you add more layers with pre-training, it's getting better. Though I would say statistically it's probably not better. But at least from this point of view, it's very different than this one. And there's a missing 5 here. It's because we weren't able to train the 5-layer network. It just didn't converge to anything but garbage.
So how did you compute the variance?
The variance is this is across 500 initialization seeds.
And how did you choose? Boy, there's a lot of choices of this is the optimal number of hidden units.
Yes. Everything. So this is for the models that give us the best validation error. We estimated this over maybe 50 samples per combination of hyperparameters.
50 samples.
Yeah, 50 initialization seeds.
Oh.
We choose the best model. We start again with 500 initialization seeds for both of these. So for 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5.
So for backpropagation, what kind of optimization did you use?
It's a simple stochastic gradient descent.
No momentum.
No momentum. No. We have never found it to work really well. So. Yes, and this.
So this is just a neural network on the left.
This is just a normal neural network.
So how many? What was the optimal number of hidden units? You know, roughly for one.
For one, it's 1,000.
It's interesting because I was getting 1.53.
I got 1.06 by just changing the mini batch size. As a run
we've really tried.
No, I know. Just surprising.
It was a really. I think if you look at some of the papers that in this field, there's a lot of these sort of arbitrary choices of like, oh, we do momentum this way for this first 10 epochs, and then we do momentum afterwards. So we really try to make it as large scale as possible. So this is like probably close to like a year of CPU hour that we just wasted just on this experiment. So
yes, for this no pre-training, you randomize the weights. Did you choose many randomized weight and choose the best one to run next?
No. Yeah, the seed was not validated.
Well, you were using Yon's square root of n.
Yes.
Oh.
Yeah. Yeah, it's all, so we wanted to make it as black box as possible. So from that point.
Is it similar on training data? Like, do you see a difference between the three training?
Yeah, we'll
I think
It's a different experiment. So yeah.
I think the initialization of the weights was too big.
It does make a difference. Yeah, it does. I'll grant you that. I think somebody in my lab they've done some sort of, but it will never get. It will never be comparable. We've done.
Let's come back for this one. So MATLAB code probably is a random, whatever.
Yeah. So it's the fan-in, 1/square root of fan-in.
For some speech data, I can't get anything out of it using this.
I'm sorry?
I use that for different set of data. For this one, it probably is okay.
Okay.
But for some other data, just using randomization, it doesn't really get.
Well, I think you have to have the right kind of combination of your inputs. I mean, it's a choice. You have to choose. So this are with sigmoidal hidden units. So your basically your weights have to. If your data is kind of mean 0 and variance 1 or something. Your weights have to be chosen such that they kind of the activation of your hidden units follows on average at the beginning in the linear part of the sigmoid. So it's a choice that depends on the data. First, you have to kind of make your data play well with the sigmoids, and then the weight kind of initializations have to be, as you said, 1/square root of the number of inputs.
And one more nitpicky question. I'm sorry. Did you initialize all the layers randomly or n-1 layers randomly?
By what's the nth layer?
You don't need to initialize all of them randomly. You can choose one layer to be 0.
Yeah, it's true. No, we initialize them all randomly.
I have a question. So it looks like, so you're adding more layers, you're making the model more and more complex, and this guy is getting worse.
Yeah.
This guy is.
Yeah.
So that would be the classic effect of a regularization scheme. So the question is, I don't know much about the left-hand side. Is there any regularization here at all?
We've validated that parameter as well. So we've done like L1 or L2 kind of standard shrinking or just the L2 kind of regularization. So we varied that parameter as well.
Shrinking of the steps.
Oh, not of the. So you add a penalty to your cost, which is lambda times the L2 norm of your weights.
With the entire thing.
Of the entire thing, yeah. Or layer. I mean, it decomposes lower to the.
And the same. And so that's non-zero, and it's the same for all weights.
It's the same for all weights, and it's on. You mean the optimal one? So for each of them, it's gonna be very small. But yeah, there's a non-zero optimal lambda for
applied to
that is applied to all of them. Yeah, and it's early stopping. Yes. And I think the mini batch size was also validated, but we didn't do like very fine grained. Like it's either 1 or 2, 1 or 10 or 20. So.
Okay, what's the mini batch size for that pre-training?
Yeah, it's the same thing. So you mean the optimal one? I think it's 10.
10?
Yeah. Though.
Well, 10, I guess something similar, but you get a 50, 60, you get better. I don't know.
Yeah, I think if you're gonna pound on it more, if you were really to find the truly optimal hyperparametric selection, I think what we wanted is more of a qualitative effect of what's going on. So I think you can make this lower. You can make this. I think you can subtract probably safely about 0.1 or 0.2, but not for these.
I haven't tried.
Yeah. So I think for one layer, maybe you can get there. I think 1.5, I'd say safely. But these can get 1.3, let's say. And I haven't really tried too hard. I mean, it was a simple experiment where I launched a batch of jobs.
So you think that the reason why 5 layer, the error
here,
the right hand side,
here
it goes up is because the
well, there's an optimal kind of number of yeah. I mean, there's obviously if you add very, very many layers at some point in time. It's kind of a classical trade-off between the complexity of your model and the kind of data that you have. So at some point in time you're going to overfit, even if you have a really good initialization point.
To be less severe for deep.
That is correct. Yes.
The shallow path.
Yes, I think that's basically the conclusion from this mark, and you can see this also from the tail here at the so it's not like you get I got a lot of these. On this side of the distribution, so it's more the errors. There's a bit of a skew towards bad errors. So it's more likely to actually get into a really bad local minimum or generalization minimum if you want. If you have one of these networks without retraining, than one of these. And it's once you get to worse results, you get the same kind of effect here, but it's less pronounced than in this. So like you can see some of this of the kind of a histogram of errors. So this is for one layer, this is with pre-training and without pre-training. So this looked like a bit of Gaussians. This one has a bit more fat tail, so this is with 4 layers. So this corresponds to this distribution here.
So just curious, when you run either case,
Yeah.
Is it true that all the training error is 0?
We'll get to that
Is it okay?
in 1 second. It's true.
For this case,
But if you're looking at the classification error, which all these networks get 0 classification error for training, so it's hard to compare. We're going to look at the actual training objective, which is more interesting. So yeah, we've seen the effect of pre-training for the generalization error. Another kind of effect that we're going to look at is a bit more conceptual. Is we're going to try to look at the actual networks in what we call the function space. So we're going to try to project the networks, the outputs of the networks. We're going to treat them as functions. We're going to try to project them via some nonlinear dimensionality reduction to 2 methods, actually, to a 2-dimensional space. So each of these points here, each single point for different colors, represents one network at one point in time after one epoch of training. So this kind of, we call it the flower, it represents neural networks pre-trained using unsupervised learning. I think it's RBMs, 2 layers. So this is 50 networks after one epoch of supervised training. So they all kind of start in the same point, and they all kind of move to their local minimum as unsupervised learning goes. Yes.
What is the x and y coordinates?
They are arbitrary. Yeah, they have no meaning. So this can be rotated in any way. So there's no it's just that it's the result of either t-SNE, which is it's a dimensionality reduction method that kind of preserves local structure, or isomap, which is dimensionality reduction that preserves kind of global structure, and it's whatever output, whatever values these methods give to you. I don't think they're meaningful in any way.
Yes, for the deep network, you compose with all the weights across different networks.
No, these are not the weights. So this is slightly different. We're going to get to the weights in the next slide. These are the actual outputs. So you take a test set, you compute the output of your network on each of these of your testing points. You concatenate this gigantic output vector. This is your input space, if you like. So this vector represents one function at one instance at one point in time. You're going to do this. You're going to take a bunch of these, so 50 networks that are pre-trained, 50 networks without pre-training, so randomly initialized. You're going to put them in a big bunch of basically vectors that have dimensionality, I think 100,000 or so. And you're going to project this. Of course, it's impossible that this preserves all the right distances, but at least kind of it presents an interesting picture of what happens if you project all of these vectors into 2 dimensions, and you look at the evolution of the networks as you continue supervised training. So there's a couple of interesting things that you can observe here. One is that they seem to explore different kind of regions of space, but they don't seem to kind of cross each other's paths, if you like. And with isomap, what's interesting is these are networks without pre-training, and this is with pre-training. From a point of view of a network, of one of these networks with random initialization, the volume occupied by basically all the networks with pre-training is very small. What else is here? There's many apparent local minima. So if you look at, this is a network. This is so it's a bit of an artifact of the method, since it preserves local structure. So it tries to kind of cluster things together a bit, but it also means that these kind of tiny things. So this corresponds basically to the trajectory of a network in this 2-dimensional space at the end of training. So they all seem to go to the same kind of.
That's MNIST data.
This is MNIST data.
So
yeah.
that is the output will be just number 10 points.
This is 10 points. Yes, this represents the class probability.
From 10 to 2.
No, this is
times 10,000.
10.
Oh, I see.
So the test set, yeah. So the test set is 10,000. You compute 10 output labels, basically, or not labels, but just the class conditional probabilities, or the log of these. You concatenate them. You project.
So, but I question whether you can take the volume of the projection and try to interpret that, because it could be the volume, how tightly clustered they are, could be side effect of your of isomap. Right? So I mean, like.
Well, we tried here to make one single component. So it's so that's the kind of input parameter that we gave to the isomap. So it will. I agree. It's not.
Right. I think looking at how disjoint they are is probably still meaningful. In that it's probably not an artifact of your nonlinear embedding method, but like looking at the volume, that seems because.
I mean, that volume is yeah. So
I've seen plenty of examples where you take like a uniform Swiss roll and you unroll it, and if you don't do it right, you can get this kind of.
Well, that's why we did this. We tried a couple of these. So we tried PCA also. We tried like kind of a linear projection method, and they also they go on different paths. I didn't.
So these are on the same data set, two different.
This is the same data set, two different methods for nonlinear projection, nonlinear embedding.
But just think about it. 100,000 points and collect up to 2 points. You see, there must be a lot of noise there. So the question is that what kind of variance is the noise?
Wow.
That makes it overwhelmed. It's just like I don't know detail about this technique.
Yeah, it's. So we've done, as I said, I think the main conclusion, what we tried to see is whether the motivation for this experiment was that do they seem to explore. Basically the hypothesis is, well, if I try long enough, if I try hard enough and randomly sample from this uniform, maybe bad way of sampling, weights in my randomly initialized network, but will I just get lucky and get one of these, one of the pre-trained networks? It's a hypothesis. It's a plausible way. Maybe it's, pre-training is just a way to kind of choose some of this under the good random initializations. And I think basically the result is, at least as far as we can see, I mean, admittedly, I'll admit to, there cannot be any perfect way to project from 100,000 dimensions to 2, but at least from this point of view, they don't seem to kind of explore the same kind of regions of space from this function space approximation.
Different points over there, you just use different seeds, I suppose.
Different points are different seeds. Yeah, so these are 15 networks. As they start kind of in the same, because they were pre-trained, and they all. So these correspond to the 15 networks correspond to the same exact configuration of hyperparameters, but just different random initialization seeds. So, any other questions? Yes.
Do you know how significant the effect is of the distribution of unsupervised data being correct? Basically, if you had experiments where you would try to distort the distribution or say noise the unsupervised data.
Well, you can always make it. Like clearly, you can always be adversarial about it and make unsupervised distribution clearly unrelated to P of y given x. So then you're going to be wasting time. But yeah, here it's.
But how sensitive is the result of?
I don't know. I don't think we've got any confirmation of that. Yes.
Just to make sure I understand, these two flowers.
Yeah.
They were so the projection onto the two-dimensional space was done independently.
No. Both of them at the same time.
So why don't they start at the same place?
Because one of them. These all networks have been randomly initialized. Randomly initialized with standard neural networks.
So how does your random initialization all start at one point, basically?
Well, they all start at the same kind of random point because they all have the same kind of same hyperparameters. So they all have 1,000 or whatever hidden units and.
It's not just the initialization point that's part of the data. It's also the output.
It's the prediction distribution.
We're not projecting the weights because it's not a good idea to do that. I mean, you can always permute the kind of the hidden units in the network, and it's the same solution. So that's not. So there's many configurations possible that it's misleading to project the parameters of the networks, but the outputs of the network should be independent of the way.
I don't understand. Why isn't it reasonable to ask what would a standard neural network do if it started from that point with a black circle?
Well, I don't know how you would make it start from there. I mean, these are standard networks that randomly initialized. Well, of course, you always randomly initialize. You do unsupervised pre-training. Then you do supervised pre-training, supervised learning. So you've done the unsupervised. You've modeled P of x. You've gotten your parameters. You compute the output of this network on your test data. This is where you are at the beginning. and then you move. Here, you've done no unsupervised learning. You start randomly. You compute where you are in this projected space on your test data, in this function space. And then this is where you are, this is where you go. Is that clear?
You're saying so this basically means that no matter how you initialize, random kind of covers the space uniformly.
No, but it's
never start there.
It's random with. So they all have in common that they are the same hyperparameters. They all have the same architecture, the same number of hidden units, the same learning rate, the same regularization factor, the same mini-batch size. The only thing that they differ is in the initial value, in the random seed of the weight matrix. So
they're initialized to be linear, whereas the other ones are.
But the hypothesis space for these guys and these
No,
guys.
wait, you're right. A random network could eventually be there, but it's so improbable that.
Yeah. I think that's the hypothesis. Is that it's so improbable that it was here. It could theoretically be here, but though it's not even clear because the way we initialize this uniform over the actual values are bounded to be minus some small number and some small positive number.
So it's a linear number. But the other one's doesn't have to be. The other one doesn't have to start linear, right?
Oh no.
It's whatever crazy thing.
Whatever DBN spits out is where we are here, and these are big numbers.
Same hypothesis space, at least for initial.
Now, for each point that you finally end up with after supervised training, do you have a measure to see how good those weights are?
Yeah. So these are the networks. These are the networks that so for the class, this is the best randomly initialized network, best 50 for 2 layers. This is the best pre-trained network. So these are best in class. So they go to the whatever.
So you have a plot to show.
Yeah, we'll get to the training. Yeah, we'll get there too. Yeah.
I have a question. Is there a way for you to say just say unproject? Is there a way for you to just unproject in 2 dimensions, point to an original weight space, and say what would happen if you say started in one of the after you train you have that little bloom thingy. What if you started in that region?
Well, I think the only thing that you can do is I don't think you can unproject. No, I don't. Not with any.
Because it would be interesting to see, if you started in that bloomy region over there to start with.
You mean this one, or?
Yeah, for this one, it goes.
Oh yeah.
If you started closer to where the eventually ended up to begin with, would you just get even better results?
So we'll have some sort of experiment that is kind of like that, where we start with the same kind of values. So not obviously, yeah. So we say same kind of magnitude of the weights that is given to you by pre-training, but random. So not the result of the unsupervised learning. And we'll get to see. We'll test a hypothesis that is very similar to what you just said.
Okay.
Now we can't just back project.
So maybe we should keep going because we've.
Yeah. Well, you have.
We have until noon, so don't worry. You don't have to finish.
Okay. Well, yeah. This talk was supposed to be 45 minutes, but yes, we've been spent 10 minutes on this one. Okay. So the other way of looking at it is the actual weight space. So you don't take the output of the networks on your test data. You actually just look at the filters, weights, I don't know how they call those. Receptive fields, exactly. Yes, there's many words for that. So basically, since we're operating on images, you just take the weights and the first layer weights, and you make them a nice image in the same space as your input space. So you actually can see. So white corresponds to kind of positive values of your weights. Black corresponds to negative values, and gray corresponds to 0. So a couple of interesting things in here. So this is with a DBN, the first layer weights. After pre-training, so after unsupervised learning, this is what they give you. So it's some sort of edge detectors, stroke detectors, whatever they are. It's not necessarily interpretable. This is what happens with the same network. So after you've done supervised learning. So there's a pretty small difference between, at least kind of visually, if you look at have the kind of a visual inspection of where these weights ended up after you've done supervised learning, they don't seem to be differ much at all. Conversely, these weights, this is obtained with a 1-layer network, well, with a 3-layer network actually, without pre-training after supervised learning. So the comparison is between these. So they're not necessarily in the same kind of regions of space, visually speaking. It's not as strong of a statement that I said with those trajectories. But this is interesting. What this shows us is that unsupervised learning kind of really constrained where you start from. the kind of features that you're going to be starting with in your supervised learning, and where you're going to end up, which is basically in the same kind of basin of attraction. So I have this cute little method for visualizing second layer weights and kind of third layer weights. I don't think we're going to have time for that, given how this has gone. But it's basically a way to figure out what is the kind of the maximal input that you're going to get for each unit in your layer. So the interesting thing is that there's a couple of the difference between what happens after unsupervised learning and after supervised learning is increasing as you add more layers. So it's increasing, and there's basically nothing in common here. So there's one thing interesting here. They basically become kind of digit detectors here.
So why should the higher layer weight give you something closer to the input? I thought.
Well, they become, so in a sense, these are more complicated features, right? So
these are the weights that he's displaying.
Oh, no, so this one, so what's that? The first one is the weight.
These are the weights, yeah. This is the second weight. These are.
So receptive field. No.
Yeah, it's a receptive field, but where you take each unit, and you say, find me a configuration of the inputs that will maximize the activation of this input.
So that's not weight.
It's not a weight, but you can consider if this were a one-layer network. This is in a sense.
It's odd that they're all white.
Because we're really cranking, so it's a kind of a it's the optimization.
No, I understand. But why aren't there black and white ones? I don't know. Oh, we can talk offline. But
yeah, it's really just an artifact of the fact that we are maximizing the function. So so it can put a lot into the white. So because it can basically it's a maximal input. So and since this pixel, if you don't bound the norm of your whole thing, can contribute a lot to the activation of the function. Either way, there's some funny things here happening. This is what looks like a 4 detector, transforms into an 8 after supervised learning. So
these are just randomly chosen.
Yeah, this is just So these have like a
50,000.
Yeah, this is like each layer has 1,000 units. I just chose it without any. It's the first. I don't know how many, 100 or so. So we've seen the effect of pre-training. Now we're going to try to more get to what pre-training actually does. I think we've seen a lot of hints of regularization, and we're going to see a lot of this in. So I'm going to get back to just what you just said. So if you're about this hypothesis, the simplest hypothesis actually, about not the regularization or optimization hypothesis, what we call the conditioning hypothesis, is perhaps what is just going on is, well, you're trying to simply what pre-training gives you is it gives you the right range of values for your weights. I mean, if you think about it for more than 5 seconds, I think it's a pretty silly hypothesis. But perhaps what just happens is it conditions your supervised learning in a kind of the right way. So what we're going to do is with this experiment, we're going to try to simply compute the marginal distribution of the weights that is given to us by unsupervised learning. It's some sort of Laplacian-looking kind of distribution. So it's fat-tailed. So there's a lot of large kind of values possible. And we're going to just sample from it. Instead of randomly initializing from the standard kind of Yann-Lequin way, 1 over square root of the Fanon, we're going to sample from this Laplace distribution or fat-tailed distribution. And it's interesting that it actually gives you a bit of a boost. So this is with random initialization. With this histogram initialization, as we call it, and this is with pre-training. So this is just the classification error. But it clearly cannot account for the whole difference between what pre-training gives you and what
You're sampling from the distribution like kind of independently, right?
Yes. So this is not. We didn't push it too hard. We didn't want to build a multivariate distribution of the weights. It sort of defeats I don't think it's a very interesting experiment. Perhaps maybe it actually if you actually did this, but it's pre-training really what it gives you. It gives you large values of the weights, but they're not randomly sampled large values. They have tight correlations between them. So because they need to reproduce the data well. So this is the plot that many people have asked me already about. So this is. If you more directly find the role of pre-training, is you look at the training error versus the testing error kind of over time. So you take 2 networks that have the best hyperparameters, so the best validation error, You train them until they converge, until there's basically no more change in the training error anymore in the training objective function, or at least as far as we can see, there is no more. We are at kind of a local minima, or we don't improve anymore. And you look at what happens with pre-training, so in red, and without pre-training. And it's interesting that you never quite get the same kind of training error. So this is the training error. You never get it. And this is lower this way. The networks with pre-training never seem to get to a better local minimum in kind of the objective function. This is the cross entropy, by the way. So it's not a classification error. Classification error, they all get to 0 very fast. In training, so there's no point in actually measuring it. And this is the test NLL cross entropy. So it does fit kind of a regularization hypothesis pretty well, a regularization interpretation at least. Because it trades off training, so it trades off the capacity to overfit for a better generalization.
For that experiment, I think it would be nice to note one single number. That is, if you do infinite amount of randomization, one of them must be better than that one.
You mean which you're looking at this?
One. Well, the one in the blue.
Yeah.
So the question is how many choices have you in randomization?
Wouldn't they both be
for
perfect on the test set if it was literally infinite?
Well, the real question is that what kind of exploration you might want to have in the randomization that somehow will get something close to this or even better.
But the point is that with pre-training you don't need to do that. I think that's you don't need to infinitely sample.
It's not the best. Well, the question is how much you need to explore. Right?
Yeah, well,
the size of network is small.
We tried more than what a normal sane person would do. So, so I think that's.
That's fine now. So you can go ahead.
Let's just say that I think I took down Google Maps for a couple of hours. So with my exploration of these things, people were not happy. So I think that's about us. 500 per combination of hyperparameters, and then you have number of layers, number of units per layer, learning rate, batch size, regularization parameter. Each of them have like
enough effort. Nothing can do anything.
Yeah, I think from at least I think there's also we haven't tried like different is it sigmoid versus tanh or other types of nonlinearities, different kinds of. You can play with this a lot.
But the sense is nothing can be.
Yeah, I think I think the main argument is not the difference between these on the test level. I think you can make this a bit smaller, maybe. But this really we tried hard to see whether a pre-trained network can actually achieve the same training error as a network without pre-training, and it cannot. Another argument for regularization is, we said, if you think of pre-training as in some sort of way, kind of vague way, constraining the capacity of a network to do regularization, maybe that's what it does. Maybe if we did another classical way of constraining the capacity of the network is to constrain the size of the hidden layer. So we just did that. And then we see whether pre-training, what kind of effect does pre-training have in that case. So what we did is, as I just said, we took 1, 2, 3 layer networks. It's the same result basically for all of them. And we varied the number of units per layer, which is kind of constant. And you can see that, so in black is a network without pre-training, and in red and in blue is with DBN or RBM or denoising autoencoders. So it's the same kind of curve. You can see that if the number of units per layer is small enough, pre-training actually hurts. So it seems like pre-training acts as an additional kind of regularizer to the one that's imposed to you by the capacity that you're shrinking with the number of hidden units. So it's one way of doing it. So we've had these results. We've had some other results. I'm not going to talk about them, but they're interesting. But as somebody pointed out, if pre-training is a regularizer, and what it does is basically it just defines the starting point of your supervised optimization. Perhaps, like some other regularizer that you might think of, perhaps its influence will disappear as you have enough supervised data. If you're a Bayesian kind of person, you think, you have a prior, which is defined by the unsupervised learning. You have some likelihood term that comes from the data. your prior is sort of maybe not data dependent, so it will be overwhelmed by likelihood if you're, if you train long enough, if you have enough data. So we said, well, let's just verify this hypothesis. Let's just see what happens in an online setting where we have enough supervised data that we clearly, if this is true, clearly it will, whatever starting point we start from, it will not matter at some point in time. So we did this infinitumness, this 10 million example thing. And basically here it's the number of examples seen. So this is in millions, so 10 million is here. We've tried with 30 million as well. It's the same plot. There's nothing different. Except we couldn't try some of the models. They're too slow. And we measured the online classification error. So the only difference between the black curve, so the dashed is one layer with random initialization, and the solid line is 3 layers with random initialization, and the red curve, which is a 3-layer with denoising auto-encoder initialization, so with pre-training, is the starting point, where it started from, which is the outcome of pre-training. Yes?
So with online classification error, it's not the regret. You're doing something.
Oh, it's just a classification error on the next example, smoothed over time. Over the next.
Oh, smoothed over time.
Smoothed over.
So you're not integrating.
No.
Okay.
I don't.
Yeah.
I've trained on 1 million examples. I test on the next 100,000. I see what the classification error is. I go on. You can see you get some sort of ridiculous classification errors, 10 to the minus 5, because there's so much data that you can get to pretty low. So
well, I assume this is because it's actually the same data that's been slightly perturbed, because otherwise it would be the same as your test error, wouldn't it?
Yes, in a sense, yes, basically. But so here we've done 2.5 million examples of unsupervised learning. With the red curve, and 7.5 million. So we've sort of set a budget of 10 million examples. And either way, even if you allow this network to continue, the network without random initialization, to continue, it never quite gets the same. It gets like this. So they're not clearly the starting point of this non-convex optimization problem, which is finding optimizing this deep neural network. Clearly, it matters. So even in a scenario with essentially unbounded training data. It's a bit surprising as it doesn't quite follow the standard interpretation of a regularizer. If you actually did this, and I did this experiment, if you did an L2 kind of regularizer, the optimal value, you have a lot of data, is 0. There's no reason to use L2 regularization or any of these kind of data-independent regularization schemes. Well, the very simple canonical regularizer. I mean, maybe something that's like, minimizes sparsity of your activations or something. It's maximum, whatever. But it doesn't follow the standard interpretation of a regularizer, which is what people think of.
I think it's pretty clear that this is because your data isn't real data. I mean, otherwise those numbers wouldn't be so low.
Oh, yeah. So I've done some experiments with more real data where we actually have like a kind of IID 1 million examples, and it's the same kind of result. So there's no difference in there. But this was published, and that one not. Any other questions about this plot? Okay. And it's funny that you look at this and okay, maybe it's a regularizer, but not quite clear why. But the training error, if you took the models that you get at the end of training, so you've done 10 million examples, and then you test them on the same data that you've trained with in the same sequence. This is a network without pre-training, and this is a network with pre-training. So even then, and there's a couple of things. It's better at classifying things that it has just seen. That's just how gradient descent works. And for these examples, these are essentially basically like test examples. They're far enough. It has seen them so long ago that it doesn't. This error is basically the same that you get at the end of training. On the next examples. So it shows in a sense an optimization effect in the sense that it's in the online setting. It's better both at the training error as defined by this. Actually, some of us expected these lines to cross. Somehow you would think that maybe a network without constraints, such as the one that's randomly initialized, maybe you would overfit more on the data that it has just seen, especially if it has a lot of tunable parameters. But these networks, the pre-training seems to have done an effect here too.
What is there a sharp drop?
Yeah, this is testing on the same sequence of data that it has seen during training.
Oh, I see.
So these are the very last examples. This is where the gradient descent moved. It's the direction where the gradient descent has just moved it. So it knows how to classify this pretty well. It's surprising that it's not 0, but it's computed over a large enough sample that it will not actually be 0. I think so. I'm getting to one of the last results, and one that I think makes the clearest and strongest point for why pre-training can be seen as regularization is, well, if the starting point of your optimization actually matters, why don't we just do an actual test of the, if you vary the way you start from, but not from the parameters, but the actual data that you look at the beginning of training. So you take the same 10 million examples that you've seen, but you vary the first million. So you keep the 9 million that you've seen the same, but you vary the first million that you look at. And then you observe what is the variance of the output of your function at the end of training. So basically, you're just computing a score of how sensitive your estimator, your classifier is. How sensitive is it to the data that it sees in the beginning? And what you should be comparing with here is this point on the red line, which corresponds to the start of the optimization of the supervised learning for networks with pre-training, with this point, which is a randomly initialized network where we vary the first million examples. And we can see here the pre-training, so it has, it has done unsupervised learning, and it kind of doesn't matter which examples we see, which supervised examples we see in the beginning of supervised learning after we've done unsupervised learning. The variance is going to be low, or much lower than the variance that you get with a network with random initial weights.
And this is variance in the log of the output?
Yes. Log of the correct class.
Log of the correct class.
Yeah.
You're using multi-domain.
Log softmax.
Yeah.
Yeah, so you group this work piece of called the curriculum learning. So is
yes.
Part of this kind of.
It's future work. Just put it this way. So it's one of my slides. But curriculum learning, I don't know, for those that don't know, is Joshua's idea that if you order the examples, you have some sort of non-convex optimization problem, and you order the examples that you look at from simple to hard under some sort of metric that is somehow defined. Then in a couple of problems, image recognition and NLP, I think it's joint with Ronan Colobert and Jason Weston, they obtain better results. With NLP, they just basically increase the vocabulary size. So I think in a sense it's sort of, this is what it says basically.
But this one doesn't really order the importance.
Yeah, it doesn't really order. But this one basically says to you that it's a gradient descent, stochastic gradient descent is very sensitive to where you start from. So, and the early examples influence more the where you're going to end up. So you should pay attention to where you start from, and this reduces the variance of the output that you're going to get at the end of training. So you can see pre-training as variance reduction, which is, I guess, another quality of regularization.
So this is result obtained by 10-minute batch sample that you talked
Yes.
about.
Yeah. So this is the networks that are best in class again. So, yeah.
I apologize. Can I take you back one slide, please?
Sure.
We went kind of quickly on that. So you were saying, and I think very correctly so, that you were expecting the blue line to
intersect with the red line.
Intersect and to get, be lower at some stage, and you don't see that here.
Yeah.
But then you said, I don't know, you didn't really explain that. So this to me is a red flag. I mean, this means that, so this is kind of the whole problem with an empirical observation, that you have to, trust you that you did a good job in training your competitor good enough, and this kind of says that maybe.
Well, this is this is the network that has obtained the best validation / test error, if you like. So this is the one that, well, I mean, you can trust my honesty or not, but I tried hard enough to make it.
I'm not questioning your integrity at all. I mean, I'm just saying, this to me would be a red flag that would say something is wrong in the experiment.
I don't understand what the red flag.
Well, why is it a red flag actually? I mean, they're both equally, for me, they're plausible alternatives that they cross or not. I mean, I don't see why. I mean,
I think the natural intuition would be that the unconstrained thing would, ultimately on the training data get better.
Well, this is not, but this is just on the examples that it has just seen, right? So it's.
Yeah, still, I mean, when you constrain less, you're supposed to get.
But you're only constrained.
You can do better.
You're only
It's a local minimum issue.
Yeah.
You got into the wrong basis then, or
Right. Especially with these nonlinear models.
That's called explaining away. So you're,
No,
I just correspond. You're giving me.
Well, okay.
We need the hypothesis before doing the experiment. After that, we can.
Well,
you can find explanations.
Well, except for neural networks, I know a priori that the hidden units get wedged because the gradient gets multiplied by the activation times 1 minus the activation if you have sigma 1. So very little gradient affects the bottom. Once you train them, they're wedged. So it's not truly an online experiment because really the parameters of the first layer get set very early in the process. And so those probably get screwed up. In fact, he showed pictures and they get kind of screwed up.
Yeah.
And you're screwed. So it matches my a priori. I'm not explaining.
Yeah, I think so. The reason I said I've even mentioned the crossing is that it was one of those. We actually before we doing this experiment, we said, oh, what will happen? Like we like to do this in the lab. I like to enforce this, because there's a lot of this hypothesis after the fact kind of dealing, which I don't like. Like, oh, we observed the data. Oh, let's make a hypothesis that really fits the data. So I like to say, somebody says an idea, and then they're like, well, and I like to ask the person, show me what you think will happen. Show me this graph, for both of them, and I'll put mine, and I'll try to make an argument for why I think this will happen, and the person will. And one of those hypotheses was that, and it was something along the lines of what you just said. Like because it was unconstrained. I don't know. This is what we observe. As far as I can tell you, it's also I predicted this would happen, and I did the experiment, so it's not quite fair. But yeah, we can talk more. So, anybody has questions about this? All right. So, final plot. Courtesy of Joshua, though he said that if I say this, I should not use it. So basically, it's more of a kind of a mechanistic explanation of, and it's along the lines of what John just said. It's the dynamics of unsupervised pre-training initialization is such that, in 2D, you basically at the beginning of the training, you're choosing the kind of quadrant or hyperquadrant that you're going to end up. Your weights are going to end up, and it's going to be very hard for you to switch quadrants, to go somewhere else afterwards once you've done this. So the initial updates have a crucial influence. We call this kind of a critical period, as in psychology. So and they explain, we've seen some of those plots that the initial updates really explain more of the variance of what's going on. And this notion of basin of attraction has come up a couple of times in the conversations here. And what seems to happen is that unsupervised pre-training initializes in a basin of attraction with good generalization properties. So let's just go over very quickly. Pre-training, we've seen, induces qualitatively different functions in those flower power pictures. We've seen the weights, the weight matrices. They seem to be different. They seem to be exploring different parts of the network's space. Some of the first results that we've seen pointed towards the regularization hypothesis, the worst training error in kind of MNIST scenario, the layer capacity versus test error thing that we've seen. We try to expand those results in an online setting to see whether this pre-training advantage would actually diminish as you add more data, and it doesn't seem to. There's some caveats, as we've seen. Pre-training seems to be a variance reduction technique. We've literally measured the variance of the output. And even in an online setting, we can see pre-training as a regularizer because it does constrain where we start our supervised learning from. And it seems like in a non-convex kind of setting, this kind of constraint actually matters. So the take-home message is that unsupervised updates have a crucial influence. Explain more of the variance, define the basin of attraction. As we've discussed a bit, pre-training will have a positive effect as long as modeling P of X is useful for modeling P of Y given X. If that is not true, I'm not sure what you're going to get from pre-training. The influence of early examples could be troublesome if you think about it. If stochastic gradient descent is truly kind of subject to overfitting on the early data, so a stochastic gradient descent applied to neural networks, could it actually hurt us in a large-scale setting? If we're really wedged, if your weights are stuck in this basin of attraction that you started with, pre-training or not, doesn't quite matter. That could actually hurt you because you're going to do online learning, and maybe at some point in time your distribution is going to shift somehow, and you're not going to be able to get out of the minimum that you ended up in. Even this is all these results I forgot to mention. This is like with the constant learning rate. So there's some sort of theory that says stochastic gradient with constant learning rate should be able to escape kind of local minima in a sort of a sense. Anyways, we have a relatively fresh, as in it was just published, JMLR paper that has more. There's some future work. We want to understand some other semi-supervised deep approaches. For instance, there's a lot of people, namely Andrew Ng and others, who use cases where there's much more unlabeled data than actual labeled data. It's unclear whether some of these results that we've said actually apply in that case. There's a couple of people who do combinations of supervised and unsupervised learning costs. So there's not a clear two-stage process. Not quite clear what happens in there too. We want to explore some connections with generative versus discriminative work, some Andrew Ng and Michael Jordan's kind of seminal work on that. Fisher kernels, which is a way of pre-training kernel machines with generative models. We've talked about curriculum learning, so it's unclear how this ties in with our results, but there's some connections in there. We want to describe in more concrete terms the basins of attraction of unsupervised learning. So what does it mean? What properties do they have, apart from being good models of P of x? So along these lines, I would like to better understand the kind of invariances and features that are learned by unsupervised learning. So I think that's more of a concrete statement than just basins of attraction. It's pretty vague as a term. So I think we need kind of a tool for visualizing or comparing, maybe the strategies that you use for pre-training, the costs, the architectures, and a tool for better understanding, maybe poking at those networks. And I have a couple of those tools. You can talk with me if you want to. It could be useful to maybe think, so this is one of those. So we've seen those features that I've just showed you. So I've done some work on trying to visualize that a bit more. And maybe it could give us a more definitive answer to why is it actually hard to train a deep network, and why does pre-training actually make it more easy. So I think that's it. Right on time.
Besides MNIST, do you have another set of data that maybe corroborate or maybe?
Yeah, we have.
You just want more.
Well, there's one set.
Yeah, we did some. I don't know if you know about ImageNet. So this is I forgot her name. It's Stanford Computer Science. Is it? No. Is it? Oh, it's. I forgot. Anyways, it's. Is she Stanford? Somewhere in that vicinity, somewhere in the Bay Area. They collected they did Amazon Mechanical Turk. So the labeling. So they labeled about 10 million or 12 million images. And we've done some experiments with a couple of million of those examples, and the curves look kind of the same.
Is that in your JMLR paper?
No, that's not in my. No, that was we did JMLR paper. We submitted it maybe 8 months ago, so it was accepted as is. So they didn't want us to do more experiments, which we were surprised.
That's supposed regularization hypothesis.
Yeah. Well, the online setting. So we wanted to test that. The online setting is, I think, a bit more of a surprising kind of result for many people. So maybe we'll get to publish this at NIPS this year.
Thank you, Dimitri, again.